Yep, the recording is started. Okay. So come back again here. So that's the momentum, right? Again. It's a change of mass velocities. The mass is obviously constant, the same mass of that ball that you're throwing. Could be anything, right? And the velocity, initial velocity v1, final velocity v2. So mv2 minus mv1. Okay. So that's the momentum. And the impulse. Anybody is familiar with the impulse? Impulse happen in a very small amount of time. Okay. If you multiply force with the time, this is the impulse. Okay. Usually the way it happens is like you do the integration, okay, with the force and dt, and then we're going to find the impulse. So the application could be, see, like if two things collide with each other, right? It could be two molecules are colliding with each other, right? If two trains are coming, hitting each other. We have a math, interesting math like that, right? So what will happen? Obviously, we'll be dealing with this thing in design phase, right? So how strong the materials needs to be to actually construct that wagon or whatever you are constructing, right? So for those reasons. And a question with the impulse and okay, impulse and momentum. So this is our chapter, okay. And the idea here is like these are the part for final exam, okay. So chapter 15, and there's chapter 16 as well, okay. Small chapter, very small chapter. We are only in week 10, so you can assume, oh, there's one class is I can take. I did announce it, right? April, you can put it in calendar. April 15th, no class. I'll be in North Carolina for conference symposium. All right. So April 15th, no show. Okay. If you want, I can put a recording. I mean, I don't think it's necessary because we are very close to end of the syllabus. So we have time, plenty of time to finish the syllabus. These are the last two things that we are covering: impulse, momentum, and one final thing in chapter 16. Now I'll come back to this thing. So what will be happening today? My plan is to go a little bit more with some of the theory that I'll be showing in the slides. By the way, these slides are in bright space. Did you guys check? All the slides and everything is in bright space. Okay. Anyway, so once I'm going to show you those two slides that I was talking, then I have a math problem where actually similar thing that you will see. The ball is coming, hitting on the ground and going to a different velocities rather than initial velocities. Then you gotta deal with the impulse, okay, and the momentum. So that's what we'll be doing. And then I want at the end of the class we'll be talking with the homework hints. Homework number 8. All right, so these things are here. As you can see, there are some examples here. Okay. Uh, so okay, so application. Yep, this could be some application about the impulse. Okay, linear impulse. Okay, what happened? How can you determine the magnitude of the linear impulse applied to the fender? Okay, as you can see, could you analyze the carpenter's hammer striking in a nail in the same fashion? Okay, a hammer is coming with the impact happening here. So this sort of thing is the application. You see, if you are hitting a baseball, is this baseball? You guys saying is it baseball? Yeah, baseball by bat. Okay, so yeah, what would be happening here? Some more application. Read through that interesting stuff. The slides are over there. Okay, but this is what important here. Okay, the equations that we're seeing here. Okay, first start with the linear impulse and momentum. Principle of linear impulse and momentum. So principle of linear impulse and momentum can be obtained by integrating the equation of motion, okay, with respect to time. So that's what you're seeing it here. No, here. That's the equation of motion, right? We've seen it all the time. So from here to here, what we're doing, we are putting some limits. So for both velocities and the time, right? You're doing integration in both sides. So basically, for left side, where you have the summation of forces, you're doing the integration with respect to time t, okay? So you have the upper and lower limit time t1 and t2, and velocities are v1 and v2. Those are upper and lower limit. And you'd be finding this impulse equal the change of momentum. Do you see that? Okay, it does make sense now. All right. In other words, if you'd like to be consistent with the unit, right, just dig through this, okay, where you have this thing and this thing are kind of equivalent. I'm going to do it again. So F multiplied T, we're doing that, right? the force multiplied time. So I'd like to see that is same. So this is impulse, remember that, right? And this is momentum. Momentum. So we'd like to see if the units are consistent. So force unit, you know Newton, right? And that is time. You know Newton equal what? Kg meter per second square. Everybody remember that? All right. So you have this kg meter per second. Now come back here. This m is mass kg and v velocity is meter per second. So those are consistent, right? See that? So yeah, that's the relationship. All right. Seeing some of you taking classes, take your time. I'll just move on. All right, perfect. All right, so this idea is going on here. You see here. So what if you don't have an integration? Okay, so if you'd like to find the, you don't have a means to do the integration, means you don't have a f equation, means like you're dealing with a force which is straight line, right? This, right? So it's like the force and the time here, so which is straight line, that like this, that in other words the force is the applied force is not changing with time. Okay, it's same. So in that case the impact can be written as this way, right? Very straightforward. So for this force multiplied this change of time. So you have this t1 and t2 here. This is 1 and 2. So t2 minus t1. Okay. What if your force just follows a curve? Okay. In other words, you have a variable force here. Then obviously you must have to do integration, right? You need to know the equation for the force with respect to time, right? This is a function of time. So you need to know that. So then you can do this dt. Okay, that's your impact. This is just a way of showing how to find different impacts. Any question? Is good so far? These are very easy stuff. And there is the unit consistency. Dig through that. You know, slug and kgs are equivalent, right? Or pound mass. That's it. And then I have the math. Any questions so far? That's good. Should I move on? Perfect. This is the math that we'll be solving today. Take a look on this math. Read through the math. So what we're seeing here, a ball is striking on a ground with the angle of 45 degree, right? And the initial velocity of the ball is 25 meter per second, and projected velocity is 10 meter per second. The angle is 30 distance, right? So these are givens, and the ball weight is given as like 0.5 kilogram ball, right? And then you got to find the magnitude of the impulse force exerted on the ball. Magnitude of the impulse force exerted on the ball. So that's the problem here. See, we know impulse is force multiplied time. The time is not given, but they gave you what, like the velocities, initial and final velocities, the angles and everything. Then the mass is given. So you'll be finding change of momentum to find the impulse. That's the theme I'm trying to establish, right? Everyone? All right. So if that's the case, then we're going to go in that direction. Okay. So the strategy, let's talk about it. So you're going to draw momentum and impulse diagram first. Okay. I'm going to show you how to do that. Okay. And apply the principle of impulse and momentum to determine the impulse force. The principle of impulse and momentum, we've seen that, right? The F dt equal F m del p, or change of velocities in this case. All right. So let's start with the givens. So m 0.5 kg. V1 is 25 meter per second. V2 is 10 meter per second, right? So find. So the impulse force F dt. Now obviously you can't write F multiplied T2 minus T1. It's not a linear F, right? So that's the varying F. That's why this is your impulse force, and you can say it is I. Now I was talking about it. You don't know anything about the force. You don't know anything about the time. You just know the mass and velocity. So that's your way around finding the momentum, change of momentum, right? So how to solve it? And the first thing first, you should be drawing the FBD or free body diagram, right, of the momentum impulse diagram. So when I'm saying momentum, these two ball that I'm drawing here is for momentum, and the other one is for the impulse. Okay, and this one is for the impulse. Okay, let's start with the momentum first. Okay, so you have these first, the striking velocity is v1, right? You can name it as v1, and there's an angle of 45, because this is the 45-degree angle, right? So you have this 45-degree here, 45-degree here, and you have these two component of this velocity, right? You have this v1 cos 45, and by the way, you can actually write cos 45, sin 45, doesn't matter, because you know the values are same for 45, right? You don't know this, so don't worry too much about this one. So this one be v1 sin 45. And then let's do the right one. On the right one, you have this mb2. Okay, and you have this angle 30 degree here. Okay, now the impulse one, that's what the most important one thing for sure, you know, there is a weight, right, for the ball itself, because it's 0.5. So the weight is the force, you know that, right? And if you're gonna, so that's the impulse one, right? If you're gonna integrate it with time, that's the impulse. Remember, this is what you learn. Everybody remember, I impulse equal F dt. That's what I was trying to establish in theory slides. Is it ring a bell, everyone? All right, that's exactly what I'm doing. So W is here force, that F and W is same. You know what is W, right? Mg. You know that, right? All right, perfect. So that's that. That's obviously acting downward. And then there is a normal force, right? Because it strikes on the ground. So there is a normal force, right? Coming from the ground. So that normal force N dt. Okay. And then you have an impulse is going to act this way, right? Now here's the beauty. Because of the weight and the normal force is almost same, it will going to nullify each other. So I'm putting almost equivalent to 0, right? Those two values, those are nullifying each other. Or the other way you can also comprehend this. You see, it says here, neglect the ball weight during the time of impact. Make sense? So in the question they gave you this info. So they said like neglect this. So in other words, this goes with this. Okay, in the question they said like, okay, during impact, neglect, because it happens in a fraction of time. All right, so then we do have the impact, free body diagram, everything here, right? Fine and dandy. And you can say you have this x and y direction unit vector. This is I, this is j, or x and y direction, either way you can say that. I can put some notes here. So this w dt and n dt, or weight and normal force, are assumed to be neglected. Very small compared to the impact of the ground. Now, in case if you're wondering, this is mg, or weight of the ball, and is the normal force. Okay, so now we have these three things in the FBD or free body diagram. Let's put the equation for them. So the equations are very simple. You have the principle. Let me write this thing. The principle. So this is the solution. So principle of impulse and momentum. So you have mv1 plus summation of. So always you do that f b dt t1 t2, doing as if like integration mv2. Now this thing, the summation of force integration of dt is always the impact, right? You can rewrite the same thing as like this is your impact mv1 equal mv2, right? Now you can say this v1 and v2, because those has two different direction, those are vector, right? I and j, you got it? And if you can rewrite this in terms of what is v1 and v2, you can write it this way. So m v1 cos 45 degree I, unit vector, remember that, plus, okay, minus m v1 sine of 45 degree. Why I have put a minus? Anyone? Any idea? Negative y direction, right? You see that? All right, perfect. So then m v2 cos 30 I, because remember this is m v2 cos 30 degree here, right? You can do the same m v2 sine 30 degree here, right? Those two components. All right, so I'll be writing the same thing here, plus m v2. This seems like a little bit crowded here, this plus thing. Let me rewrite it. Plus sine 30 j. Okay, I didn't put a negative, you know why, right? Because the y direction is going up in this case. All right, perfect. And then what's your goal here? To find the value of the I, right? Can you do that? Is the math. I'm giving you the value of the I, and I'm leaving it to you to solve it. So the I value should be 12.2 Newton multiplied second. See if you can find it. So just to give you a clue, you gotta accumulate all the I components in together and all the j components together. Once you have I and j component, you can do the Pythagorean. You know, the I component is square plus j component square, and that's how we're gonna find the value of I. Everybody might have to wait a little bit to do this class, right? Every day. All the class usually finished way before. Not for Delino, maybe, right? Delino, you have class after this class?
Just my last class. I have a class before this.
Just immediately after? Immediately before?
Yep, immediately before. Usually they let me out early, so, but
Yeah.
kind of time to take time.
This is really hard time for me. Here, 10 years almost. I never had a class like that late. Probably once or twice at the beginning of my career. I forgot now. This time today, don't go away. We're gonna talk about the homework hints, okay? I have some stuff to do today. You got it, Christian? Same result? Christian is first today. Who could be second? Christian, how are you doing with the homework? What number 8?
I did like the first two problems, but I haven't started the third one yet.
Let's start with the third one first. Then you don't have to wait here. You can go. That's the really hard to finish it first, I guess. You guys notice I put a new one, right? That one goes with this thing. Homework number 9 is already up. So one more homework is 10. I believe 2. One I forgot last year what I did. I could check. At least one is there, I know. Logan, any luck?
What?
You got it?
Yeah.
Kevin, you got it? Gavin, you got it? No.
I can't get the same one.
Lisa, you got it? Good. Alright. Great. How far you? Almost. Delina, Alin? Any luck over there? Alin, you got it?
Yeah.
Perfect. Delina?
I'm still working on it.
Yeah, still. Alright, I'm impressed. All of your performance, really good. Okay, let me do it so you can match it right with yours and do it formally. So all I'm gonna do now, just move things around, right? This I should be equal. I'm gonna kind of put all the I components together, right? And put the J components together. So that's my goal. So you can see the big picture. So the way I'm doing it, like, rearranging everything. So I have this M V2 cos 30 degree minus M V1 cos 45 degree. All right. So that M V2 sine 30 degree plus M V1 sine 45 degree. And then it's very straightforward, just plugging all the values, right? So 0.5 and then 10 cos 30 minus 25 cos 45 I plus 0.5 10 sine 30 plus 25 sine 45 j, right? These are all i's. So then you're going to do the math, right? You're going to have 4.5 I plus 11.34 j. And the unit is still Newton second, right? And then final thing would be this 4.5 square plus 11.34 square. It's Newton second, right? And you should be getting this value. So this is the procedure. All right, so everyone's ready for the homework? Okay, any question? I'd like to do a quick summary what happened here. Obviously, this is the impact and momentum problem. So I have a ball striking in the ground and then it come back with two different velocities, right, with an angle 45 and 30 degree. And then what I did is like, use the principle of impulse and momentum equation. So I had this free body diagram for momentums and the impact. And then I had the equation corresponding to that. And only catch here is like to put the velocities two different directions. Make sure you are careful with the direction of I and j, right? For example, here for v1, it's the y direction is negative j. So that's what the catch here. But once you have everything, instead of the ftt, you'd be writing I as an impact, right? And you're equating I equal or impact equal all the change of momentums, right? Once you have the I and j's are kind of grouped together, you find the ultimate value by plugging all the values like degrees, like 45 cos 45 sine, 30 cos 30 sine, and then you should be able to find the value of I and j components of the impact, and then do the Pythagorean, means like x component square plus y component square root. It should be giving you that value, final value Newton per second. So that's the summary. Any question? You got it. So homework. Delina, you were good. You need some time. You got everything. Perfect. So homework 9. Let me see. I have it here. You guys remember, like the final exam is take home, right? Okay. The exam 3 is in class, right? There are 4 exams. No meaning of you to drag you 4 times. Okay. So I'd like to give you some leeway or some relaxation during the final exam. Why I don't have the okay? Let's see if I can open it from my. What are you doing? Homework number? So. Or as I said, promise to Christian that I'll be talking with this problem first. Okay, so you can go away. How many of you started 1 and 2? Anyone? Lisa, you've done 1 and 2 as well. So after this 3, you can go away as well. Brad, you have done 1 and 2 as well. You can go as well. What about you, Gavin and Logan? No. So you have to be stick here for the whole time, I guess. That's all right. Okay, so what you're seeing here is spring has a stiffness of K. By the way, 1 or 2 are very similar problem what we did in class, right? You might have noticed. Number 3 is not. So a spring has a stiffness of K, which is, there's a typo here, 50 Newton per meter, okay, and unstretched length 0.3. So that spring, the unstretched length is 0.3. If it is attached to a 2 kg smooth collar, so this collar here is 2 kg. All right, and the collar is released from rest at A. So the collar initially was at A, right here. At rest means initially, if you assume the velocity v1 is 0, right? So think this way. So that means at initial position, half of mv1 square is 0 as well, right? Kinetic energy is 0, or t1 equal to 0. Okay. All right. So then, what does it say? From rest at A, right? For whatever reason, this thing kind of sorted out. It should be 0 meter per second. determine the speed of the collar when equal to 60 degrees. So this theta, this should be theta. I'm sorry. This should be theta. For some reason, this got distorted, whatever happened here. So this, they're asking, okay, when it is here, okay, when this angle is 60 degree, when this angle is 60 degrees, right? Then find the value of the speed of the collar, right? So in other words, find the velocity of B when it is here. So you can say this is V2, okay? If that one is V1, so that's the V2 you gotta find. Now, if you're gonna draw the sketch, that's what I'd like to help you guys first. So you have this radius is 2 meters, right? So the distance between these two is what? Anyone? Is it like 4 meters? All right, so we have a 4 meter distance between them. So let's draw a half circle, and let's put a distance like 4 meters here. All right, so this collar, it does move from one position to another position. First, the theta, when the theta is 0, the collar is here. So let me draw the collar. So the collar is here. When the angle theta is 0, and when the angle is 60, so this is it, right? So when this angle is 60 degree, or theta is 60 degree, right? So this point here, then they're asking to find at this point when the collar is here, find the velocity. You can say obviously this is V2, this is V1, right? You can say that for sure. All right, so you gotta compare state 1 and state 2. State 1 and 2. And then you have this T1 V. Remember, this is capital V1 is a potential energy, right? And then T2 plus V2. Now remember, like, this potential energy does have the spring force as well, right? Along with the potential energy, like due to the gravity. Here, this is on the same level, so you can kind of nullify that. So it doesn't matter, but the spring force is kind of act here big time. So first of all, this one is 0, right? So you have this other component. This one is half of m v2 square. You know that, right? So you have to just focus on these two components. So just follow the lead. You see, for these two, first of all, there is no potential energy for gravity, right? You know that, right? So what are those V2 then? What is happening on the collar? There is a spring attached to that, right? When the collar is at A and the collar is at new location at 60 degree, the spring stretch different distance, right? You really want me to go, you really don't want me to go any further. If I'm gonna go any further, I'm giving you the solution. I did this sketch, I'm just giving you the direction here. You don't have to deal with anything with the gravity. You remember the equation half of k. Did you remember the half of k x squared, that equation? So what is x? Anyone? That's the amount of elongation or stretch or the compression happened for the spring. Do you remember that? For spring, half of k x squared. K is what? The spring constant, right? K is the spring constant. So can you find the x? Actually, that's what you got to find for position A and position 1 and position 2. I'm sorry, at 0 degree and 60 degree. Can you do this problem now? Everyone is feeling confident? To find that, you just have to, I'd like to give you another hint. See here, that's from the geometry. I don't know how much you know about the geometry. This is a right triangle. If that angle is 30. So what is this angle, Brett? 30, thank you. You need that. Okay, from this point, think on what? Finding the spring energy, half of k x squared. okay, for these two different positions. I did give you the kinetic energy equation as well, right? That T1 is 0, initially it's 0 velocity. You guys can handle it, right? All right, so that's it. And those who are done with number 3. Those who are still struggling with 1 and 2, stay here. I'm going to give you hints, okay? Don't go away. Those who are done with 1 and 2, they can go. If you're done with 1 and 2, then you can go. If you're not done with 1 and 2, you need hints, stay here. I'm going to help you with 1 and 2 as well. Okay, while you are leaving, let's talk about number 2 first, okay? What is happening, Brad? It's not liking you.
Yeah.
Just want to stay here.
Yeah.
No more water for you
I guess so.
tonight. All right, so number 2. Okay, so you have these 3 different positions, right? Let me read through the problem first. A roller coaster car has a mass of 700 kg as a passenger. If it starts from the top of the hill at A, speed with VA is 3 meter per second. This is all distorted, don't worry. In PDF it should be all right. So it should be VA equal 3 meter per second, right? This is the velocity at A. Remember in last class, right? When we did the math problem, did you remember like what was the velocity assumed at point A? 0, right? That's the difference here. You see? So at point A, we have a velocity now. So then what? It says like determine the minimum height of H. I mean, in last problem, we did find the H as well, right? But it doesn't have these 3 loops, actually 2 loops in one case. In last problem, we just have 1 loop, right? Right. So then determine the minimum height of H of the hill crest so that the car travels around inside the loop without leaving the track. That one is same. That concept is same, right? So the car means like this roller coaster doesn't leave the track, so it's just barely hanging over there. Neglect the friction, the mass of the wheel, and the size of the car. So basically, you're saying like, okay, don't worry about anything about the wheel, the friction, okay, the size of the car. Just only care about this 700 kg, right? What is the normal reaction of the car? What is the normal reaction on the car when the car is at B and when it is C? Okay, so you have these 2 radius of curvature, right? One is for B. This is rho B. Do you understand? This is rho B. Okay, rho is the radius of curvature, and rho C is 5 meters, right? So it's like, you know, when you are in roller coaster, the toughest thing is usually at the beginning, right? Slowly your is off. Okay. So you have this thing, and then you gotta find the minimum height of H, right? Which is this, and the normal force at B and C. Okay. So all right. So that's that. So I guess what I can give you here is for okay, I guess what I can give you here. So the free body diagram when the roller coaster car free body diagram. Let me give you the free body diagram, the roller coaster diagram. So roller coaster is like that. A person is probably sitting here, right? Okay, and then the normal direction is acting down, just like in last class we've seen. The normal force is acting down, right? And the tangential direction is along this direction, and you have this along this normal force direction you have this 700 multiplied 9.81 Newton due to the weight of the car. All right, so the normal force, you can find it this way, and you can write this thing, summation of force equal MAN, right? And you can write this thing as 700 multiplied 9.81 equal this M is 700, right? This one is V square divided by rho. And this is what? When the car is at point B and point C. Till you understand? Because the load is acting down. All right. So now that you have this same thing can be used for these two different locations, right? So when the roller coaster car is about to leave the loop at B and C n equal to 0. Why? Because there is no normal force acting on the cart, right? Normal force is always coming from the surface perpendicular, right? Since the cart is now downward, till you understand, cart is like, kind of hanging, right? So the normal force is 0. That's the reason, okay? And at B and C, you have this radius of curvature was given as like 7.5 and 5 meter, right? Those are givens. Then this if you can say this one, apply this equation 1 for what? Radius of curvature at A and radius of curvature at B. Make sense? You understand? Really good? All right, so once you have those, right, then you can get two velocities. So what are those? You can get the two velocities. You can find BB and BC. Got it, Dilna? Can you find it? Think clearly and see if you can really find it. Now, if you're gonna deal with that, judging from the result, coaster car will not leave the loop at C provided it passes through B safely. Okay, so what does it say? It's like, you see, if the car leaves at point B, can the car goes at point C? If the car leaves at point B, means it falls down. Okay, that means you are on ground. So you have a fatal accident. So it is not going to go to point C. Does it make sense? So you can write this way. So in that case, this NB should be 0. So based on that argument, and that's what you're seeing it here. Okay. Okay. So then, what you're gonna do? So then you have to apply the conservation of energy. Apply conservation of energy. What are you doing by that? So you're comparing TA and BA with the TB BB. In other words, at point A, kinetic and potential energy, right, equal at point B, kinetic and potential energy. All right. So by using this equation, I'd like to give you a little bit about the VA. You guys remember, right? VA is what, like 700, 9.81 multiplied H multiplied TA. I don't want to go any further with the TA, okay? I'll just you to figure it out. So you should have like half of 700. Okay, and then you have these velocities. Velocity square, I don't want to write that velocity square, because remember, you have these velocities already at point B and point C, right? So you want to write this TB by yourself by half of MBB square. It's the same thing, right? And then you have this BV, or the potential energy. I'd like to help you on that. So it would be 709.81 multiplied 1.5. Now how I'm writing 1.5? Sorry, 15. Why I'm writing 1.5? It's 15. How I'm writing this? See, at position B, I have the height is 15. Okay, I think that's enough hints. Should be able to solve it. Can you? Okay, so finding the NC, okay. So NC would be, find NC would be, you're going to use this equation, right? So finding the NC would be what? N equal 700 VC square divided by rho. So once you have VC value, you can find the NC value. Never mind, just, sorry, I did write something more. So find NC, let me write it in clear fashion. Find NC would be summation of F equal MAN. So you have N plus 709.81 700 VC square divided by rho. So this is your NC. This is rho C. That's how we're going to find the NC. And that's how we're going to find the value of the H. Okay? And number one, I'd like to skip because a very similar problem we did. Okay? You should be able to figure it out. All right. You know, they're good. Are there any more questions? Perfect. I'll see you guys on Monday.